Trina here, and welcome back. Today we're going to be talking about times when functions are non-differentiable. In my previous videos, we discussed several tips and tricks and strategies how to find the derivative of a function. However, there are cases where it is not possible to actually find the derivative. So today we're going to cover 4 main situations that you may encounter where functions are non-differentiable. So the first case when a function is non-differentiable is if we're at a cusp. So let's look at this little diagram I drew over here. So at the point A, f of A has a cusp. Another way of thinking about a cusp is a corner or a sharp turn. So our function is actually differentiable all the way up here because that's pretty much a linear function, and then also all the way down here, another linear function. However, at f of A, we have this cusp, we have this bend. So if we think about a derivative is the equation of the slope of a tangent along the point of a curve. So at this point, f of A, how would we actually draw the slope of the tangent? Would it look like this? Would it look like this? Would it look like that? We don't know, and we can't know. There's no way to know, and that is why the derivative at f of A simply does not exist. It is non-differentiable at that point. Okay, let's move on to number 2, endpoints. So it's also not possible to differentiate a function at an endpoint. Here in this diagram, I show one example of an endpoint. This is the beginning of the square root function. And like I mentioned in the previous situation, we wouldn't know where to put the slope of the tangent at the endpoint. Again, would we put it across? Would we put it here? There's no one clear way. Therefore, it also does not exist. So we cannot find the derivative at an endpoint. So here, this is the beginning of a function. Another time where we may encounter endpoints are for piecewise functions. So let's draw one of those out. So say we have some sort of Cartesian plane here. We have a function, a piecewise function, that ends there, a jump discontinuity, and then it continues in this direction. Both of these points over here, this one and this one, are also endpoints that exist within this function. Therefore, it is also not possible to take the derivative at this point A in where there is a jump discontinuity for our piecewise function. Awesome. Let's look at the third point. So, like I mentioned before, discontinuities is another point where the derivative does not exist. So we can have the endpoint situation where we have piecewise functions, but then we can also have other situations where we have a hole. So let's look at this plot over here. So in this case, we have a linear function. However, we have a removable discontinuity, or a hole, at x equals to a. So the first thing that we can note is that f of a does not exist. So if the function does not exist at a point, then its derivative also does not exist. How can you take a derivative of a non-existing point? The answer is you can't. So that's a pretty easy thing to think about. Okay, does our function exist? Okay, it does not, so then its derivative also cannot exist. So that's another thing to watch out for. So here this is a hole, or also known as a removable discontinuity. And now let's jump into our last one. So there's also cases where we have a vertical slope of a tangent. When we have a vertical slope of a tangent, then that slope is undefined. That is this big 1/0 situation where it's simply undefined, so we cannot take a derivative if the slope of the tangent will become vertical. So one example is the one I drew out over here for you. here we have this cubic function. So this is y equals to x cubed, like we saw over here. So at the origin, when x equals to 0, we're actually going to end up with a derivative that is vertical. We're going to have a vertical slope, and therefore it is undefined. So again, the derivative exists along all other points of this function. We can take the derivative right over here. We can draw the slope of the tangent. That's great. We have a value that's defined. However, if we try to take the slope at a over here, we're going to end up with a vertical line, which is undefined. So that's something I want you to take away from today, is that there are cases where a function can be differentiable at every single point except for one. So we would still say that y equals to x cubed is a differentiable function, but the caveat is that it is non-differentiable at a specific point, at x equals to a. Same with our third example over here. We've got a linear function with a hole. Linear functions are differentiable. However, this particular one is non-differentiable at x equals to a. So always watch out for that. Sometimes there's general properties for a function, but then there's also specific cases and caveats that we have to watch out for because they render our tools like taking the derivative not possible at certain points. So I hope that was a bit of an eye-opening and cool experience for you. So make sure to jot down these 4 main situations. That way you have a great starting point so you can know how to determine whether a function is differentiable or not. If you enjoyed this video, please drop a like and comment any questions that you may have. Please subscribe for more fun and easy to follow math videos. I'll see you next time.